We've already learned how to determine the relative age of a rock or a fossil or a geologic event by comparing where it's found in relation to other objects. Today we're going to take a look at how to determine the absolute age or the actual age of the object using a process called radioactive dating. So let's say you found a fossil and you wanted to know exactly how long ago this creature died. That's what we're going to learn how to do right now. So this is all based a little bit on chemistry because it has to do with elements and atoms. We know that all atoms contain subatomic particles. They all have protons, which have a positive charge, and electrons, which have a negative charge, and neutrons, which are neutral. I'm sure you're familiar with the periodic table of elements. And when you look at the table, you'll notice that each element, the top left corner, has a number. It's called the atomic number. The atomic number tells you how many protons there are in every atom of that element. And the number of protons for an element is a fixed number, which means it can never change. Hydrogen, for example, has an atomic number of 1. And carbon has an atomic number of 6, meaning there are 6 protons in carbon always. Now, while the number of protons is fixed, the number of neutrons is not. So here we have 3 different types of hydrogen. They all have 1 proton because hydrogen has to have 1 proton. But you'll notice they have different numbers of neutrons. Different varieties of an element are called isotopes. Let's look at another one. Let's look at carbon. We said before that carbon always has 6 protons. Sometimes it'll have 6 neutrons also. But there's another isotope of carbon. There's another variety in which there are 8 neutrons. It's still carbon. It's just a different isotope, a different variety of carbon. Now the thing is, when atoms have an equal number of protons and neutrons, it's stable. But when the number of protons and neutrons are not equal, the atom is radioactive or unstable. And if an atom is radioactive, it begins to break apart in a process called radioactive decay. Here's a picture of the process. So we have this unstable radioactive atom. It wants to become stable. It doesn't want to be unstable. So what it will do is it will decay. It will turn into something that is stable. And in the process, it will release energy. This is nuclear energy. This is how we get energy in nuclear power plants. For example, carbon-14. Carbon-14 is unstable or radioactive. It will decay into nitrogen-14, which is stable. Another example, there is a radioactive element called uranium-238. It decays into lead-206, which is stable. When these radioactive elements decay, the decay happens at a certain rate, certain speed. The time that it takes for half of the atoms to decay is called the half-life. So let's say that an animal just died, and the animal has carbon-14 in it. The moment that it dies, all the carbon-14 is still there. 100% of it is there. Nothing has decayed yet. After one half-life, half of the parent material will decay. So now there's only 50% of the parent left, and the part that decayed turned into the daughter. When we add them up, we still will have 100%. After a second half-life, we're going to lose another half of the parent. So now there's 25% left of the parent and 75% of the daughter. It still equals 100%. After a third half-life, we're going to lose another half of the parent. So now we only have 12.5% of that parent material left. The rest has decayed into the daughter. And we could keep going, a fourth half-life, a fifth half-life, and so on. We just keep taking away half of what's left of the parent. When you graph this, your graph will always look like this. It doesn't matter which of the isotopes we're talking about. Now, if you're thinking this through, you hopefully realize that if we keep taking away half, we're never going to get to zero. Because if you take away a half and a half and a half and a half, you'll never reach zero. So the parent material will never completely decay, and the daughter material will never reach 100%. Now, every isotope has its own unique half-life. Carbon-14 takes 5.7 times 10 to the third years, or 5,700 years for half of it to decay. Potassium-40 has a much longer half-life. It takes 1.3 billion years for half of the potassium to decay. Uranium, 4.5 billion years. Rubidium-87, 49 billion years, a huge amount of time. What's key about these half-lives is that half-lives never ever change. Carbon-14 will always take 5,700 years to go through a half-life. It doesn't matter what you do to it. You can heat it, you can cool it, you can crush it, you can cut it in half. It doesn't matter what you do. The half-life will always stay the same. And that is the key to using this process. So let's look at a couple of practice questions. Okay, question 1. An ancient bone was found and analyzed, and found to contain carbon-14 that had decayed for nearly 2 half-lives. They want to know how old the bone is. Okay, well, we know that 1 half-life for carbon is 5,700 years. So if it has gone through 2 half-lives, it means it went through that 2 times. So 5,700 times 2 is going to equal 11,400 years. And for the last practice question, a sample of wood found in an ancient tomb contains 25% of its original carbon-14. What is the approximate age of this wood sample? Okay, so it has 25%. So I come back up to this chart. So 25% again, that's 2 half-lives. Well, I know for carbon-14, each half-life is 5,700 years. If there have been 2 half-lives, it means this piece of wood is 11,400 years old. Now, there are some other things that you need to be aware of when we're using this process. First of all, if you want to use this technique, you have to figure out which element to use. If an element has a short half-life, it means that it breaks apart quickly. And so after a short amount of time, it will have broken apart so much, it's going to be really hard to measure. There's going to be so little of it left. For example, out of the isotopes we've been looking at, carbon-14 has the shortest half-life, right? 5,700 years for half of it to decay. After around 70,000 years, there's not going to be enough carbon left to even measure. So you can only use carbon-14 for things that are not very old. If you want to date something that is very old, then you want to choose an element that has a long half-life. For example, uranium-238 has a half-life of 4.5 billion years. That means if you have a rock that formed 1,000 years ago, you would not be able to use uranium-238 because it did not go through any half-lives yet, right? It takes 4.5 billion years to go through 1 half-life. So the rock would have to be older than 4.5 billion years old in order to use the uranium, okay? So you have to think about whether you want an element with a short half-life or a long half-life. The other thing you need to think about is whether your element will be in the object that you're trying to date. All living things have carbon-14. Rocks don't. So if you're trying to find the age of a rock, you would not want to use carbon-14 because the rock doesn't have any of it. Same thing with uranium-238. That one is found in rocks, but it's not in living things. So if you have a fossil, uranium-238 is not going to help you. So you have to know what elements are in each object.